Start. I woke up to a particularly long Windows update, followed by Zoom also needing an update. Nonetheless, today for the warm-up, we have 2 items, and then I'm going to talk a little bit more about the binomial expansion. I'm sorry, the binomial theorem today, just because I kind of want to set it down into a context, like when we would care about using it. And so real quick, just to get us started into this Monday, I have a 2-part warm-up about the binomial expansion. So item number 1, x plus 7 raised to the 29th power. Obviously, I don't expect you to actually expand that out by hand. It would take forever. So here's what I want to know. What is the first term and what is the 17th term of the expansion? What the first term is, I think, is really straightforward, but it is actually supposed to give you a hint about exactly how it is that you're supposed to reckon the 17th term. And then item number 2, some binomial expansion contains 715 a to the 5th, x to the 8th. So what I want to know is what is the original expansion? And which term are we staring at? And like I said, after we go through these 2 bits and pieces to the warm-up today, I'll give y'all a little bit more context for the cases in which the binomial theorem are relevant. I'll leave it at that. You'll see what I'm talking about in a bit, yeah. Y'all ready for the last week of school?
No, drag.
Sorry, what'd you say? Was that second word?
It's becoming like a drag.
Oh, I suppose so, if you don't have plans for what to do after the school year ends.
No, I mean like this week is becoming a drag.
Oh,
like
why?
we just want school to end. Like, just get it over with.
Gotcha. Yeah, gotcha. Well, 5 more days, and I assert by probably the end of next week, you'll be bored and you'll be sad that you don't have something to do. I'm not saying you'll necessarily miss school, but you will be bored without a daily thing to do. Or maybe if you're a little bit more self-motivated, maybe it'll take more than a week to settle in. But eventually it catches up to you. Even teachers over the summer, I usually have a really good time for the first like 2 months. But by the 3rd month of summer, yeah, I'm kind of glad for work to pick back up just so that I have a reason to get up every morning again.
Mr. Robinson, can we have your personal email after school's done?
Yeah. Yeah. I was gonna do that on Friday.
Cool. Thank you.
Okay. So let's go ahead and get started on these first 2 parts of this relatively straightforward warm-up, mostly so that I can talk about the context in which we use the binomial theorem when we're like dealing with actual problems. Just because it comes up a little bit in the next section, which is the last section. But I don't think they do it justice. I want to make sure that we get a really good feel for what, like, real life context, what word problems that we can use the binomial theorem in. Okay, so item number 1. if we were to expand x plus 7 raised to the 29th power, how many terms would it have? That's not part of the warm-up, but you kind of have to be aware of the answer to that question in order to process this request correctly. If you were to expand out x plus 7 raised to the 29th, how many pieces would end up being in that polynomial? Consider the work that we did on Friday.
30.
Yeah, it's always going to be one more than the exponent. So there will be 30 terms here. So how is it that we can produce our first term?
It would be x to the power of the exponent, and then the like the constant to the power of 0, which is 1.
Yeah, so I'm actually going to write out, so in the end, our first term will simplify all the way down to just x to the 29th, but we should appreciate that there's two other things tagged on here. Off to the right, it's going to be 7 raised to the 0 because the sum of these two exponents should always be 29. We know that the first one gives us x to the 29th, but the other one has to give us 7 to the 0, so this will just be 1. And then what constant accompanies the front of each one of the terms in our expansion? One of our counting principles.
I forgot what it's called. C.
Yeah, C. So a way to count out combinations. And for the first one, we have 29. And then from that, we are going to figure out how many combinations that we can make out of how many elements. What gives us the first constant?
0?
Correct. And anything C0 is going to be 1 because there's only one way that you can reach into a bag and pull out 0 objects, and that's by not reaching your hand into the bag at all. And so this right here will give us 1. If you don't believe me, use your calculator, times x to the 29th times 1. And so our first term of this expansion is just x to the 29th. But here's why I bring this up. So it's pretty clear that the sum of these two should always be that. But the other thing that I want to point out is that if it's the first term, it's 29C0, right? So when it comes to the generation of a term, it's going to be 29C, 1 minus that number, because all of these constants are shifted over by 1. That's also why you have an exponent to the 29th, but you end up with 30 terms, because we start counting out our constants at 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, da-da-da-da-da. That's what's going to generate our 29 constants for us. So for the 17th term, what do I do? It's going to be C, and there's going to be 2 terms. What is x going to be raised to?
17.
Or is it 29?
29 and
29 and then 17?
17.
Oh, for the C part? Wait, what are we talking about? So we're going to have 3 pieces here. We're going to have the constant, which is chosen by combination, and we're going to have an x, and we're going to have a 7. So what we want to do is we want to use the pattern of the binomial expansion theorem in order to figure out exactly what shape this takes. So for our first term, what was 7 raised to?
0.
The 0. So what do you think this 7 is going to get raised to if our exponent here is 17?
16.
16. And all of these exponents have to sum to what?
29.
The exponents have to sum to 29. So if 7 is raised to the 16th, what is x raised to?
13.
So this is x to the 13. And then what about my c? What is my coefficient from Pascal's triangle in this expansion? It's always 29, and from that, what am I going to be combining? How many combinations?
16.
Also 16. It's also going to be shifted over 1 from the term in the expansion. So now I can expand out, or I can, really ask my calculator, what is 29C16? So 29, math, probability, C16. Big number, this, right?
Mr. Robinson, sorry, can you do it on screen, please?
What?
Can you do that on screen? The
Sure.
calculator. Sorry.
So it's 29, math, probability, C, 16, big number. And then that is multiplied by 7 raised to the 16, which is also a radically large number. And so the final product here in our expansion, so if you were to actually take a term here with 29 terms in the, x plus 7 raised to the 29th, the 17th term along the way, this isn't even the one that would necessarily have the biggest constant, but the 17th term is 2.255316775 times 10 to the 21 times x to the 13th power. Is that okay? So not asking you to calculate all 29 terms of the binomial expansion just to get the 17th. The binomial expansion allows us to pick out just one of them, right? Just one of the pieces in our expansion. And then item number 2, some binomial expansion contains the term 715a to the 5th x to the 8th. What is the original expansion and which term is it that we're staring at?
Is it the 13th term?
How are you getting the number 13?
8 plus 5.
So that means that's the exponent on the outside of the problem. So this is x plus a or a plus x, doesn't matter. Then raised to the 13th power. So that is the expansion. But which term is this?
Is it the 9th?
It could be the 9th term, or it could be the
6th?
Yeah, it could be the
7th.
9th term or the 6th term. Which one is really irrelevant because the two tend to be symmetric. If you think back to the numbers on Pascal's triangle, like from the middle as you work your way out, those values are symmetric, 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 symmetric. So you would arrive at this in this expansion either at term 9 or term 6 based on whether or not the inside is x plus a or a plus x. And then all we have to do is figure out in the end whether or not one of these two terms had a constant tagged on it, and how can we check that? What constant will the binomial expansion lend us here?
715.
Okay, but what process produces the constant in our binomial expansion?
Combination.
Yeah, some about a combination. So we're going to do 13c what?
I guess 9 or 6.
Or 6.
Yeah, 9 or 6. So we'll do 13c 9.
Wait, Mr. Robinson, don't you put the like a number 1 less than the place? Like how you put 16 for the first one, but it was the 17th term?
Yeah, it is one less. So it's the 9th term, which is why this exponent here is the 8th, or it could be the 6th term, which is why this exponent here is the 5th. But both of them give us back the same constant, 715.
Wait, but like for the first one, you still did 29 and then 16, even though it was the 17th term.
Yeah, because
You went one
that's-
less.
that's talking about the term while this is the exponent, I think. Right?
Oh, I see. So this should be So this value here matches the secondary exponent. So this should be 13C8. Yeah.
Okay.
Yeah, which means I wrote down the wrong term on the problem. So this is 1287, so that it works out nicely without any additional work. 1287, 13C8 is actually 1287. All that establishes is that there's no additional constants in here that are tagged on that we're unaware of. And again, it's symmetric, so 13C8 should give you the same thing as 13C5. Nonetheless, so that's it for today's warm-up. Before I talk any more about the binomial expansion, are there any questions on the homework for this section? I think the homework is pretty straightforward, maybe a little too straightforward.
So, Mr. Robinson, this was the 8th term. I'm sorry, no, it was the 9th or 6th term.
It could be the 9th term or the 6th term, but you'll notice here on the left-hand problem, when it was the 17th term, this is 29C16, and this is 7 to the 16. These are shifted over 1 from here. So to test if it is the 9th term, it's 13C8.
Okay, thank you.
But yeah, any questions from the homework? I think the homework's all pretty straightforward. Okay, so let me give y'all a little bit of context for like when it is the binomial expansion is useful to us. So in what contexts can we use the binomial expansion in statistics if that's a class that you're headed towards next year? So the binomial theorem in counting. And I'm basically just going to show y'all 2 different examples of doing this numerically that give us some usable information. Yeah. So when it comes to the binomial theorem in counting, and counting theory is just another name for statistics, because what you're doing when you do like a counting type problem, right? If you're very smart and you're like, oh, the chance of some particular event happening is 1 in 7.8 million. The thing that you're doing to figure that out is you are counting up the number of ways that it can occur in the numerator. You're counting up the number of ways that it can occur total, which would give you the denominator. And then the fraction of those 2 things can give you a rough estimate of a probability. And if there is a trick to determining those counts, then instead of doing it manually, right, and instead of like adding up all the possibilities by hand, you can use some clever scheme to quickly get numerators and denominators to combine into probabilities. When it comes to the binomial theorem in counting, we can use this used to quickly analyze possible outcomes from binary elements. And just real quick, what are some things which would have binary elements? I discussed some of these last week.
Maybe a computer, 1s and 0s.
So literal binary is one of them. However, this is good for figuring out potential arrangements of binary. It's not so good for figuring out probabilities simply because computers operate on fundamentally non-probabilistic mechanisms. What else is binary? What's the most straightforward binary probability we have?
Coin toss.
Yeah, so we toss a coin, and our coin either gives us heads or tails. Can y'all stretch and think for any other binary type events that happen in the world that we might be interested in?
Could like how chromosomes are paired?
This definitely lends itself to pairing events of various types, but that's mostly just because a pairing event can be phrased in a binary way. That is to say that if you phrase it such that you're talking about whether or not the binary event happens, right, then you can consider it to be a simply binary thing. So this is to say that you can make almost anything fit in this binary sense as long as you flatten it. And here's some examples of events which have been flattened to satisfy these requirements. Illness. Illness is complicated, but if you want to do a quick breakdown of the statistics and simply ask, do you contract the disease and get sick, or do you not? And do you remain healthy? Now, of course, to actually model the spread of a disease this way is hyper simplistic because there's all sorts of gray areas and it's impossible to figure out where it comes from. But again, for the sake of analysis, you can simply flatten disease into you contracted the disease and you became sick, or you didn't and you are still healthy. Or when it comes to accidents, the binomial theorem is used a bunch in the insurance industry to analyze what effects certain variables will have on other outcomes, because either you have an accident or you don't. And again, this doesn't take into account like the severity of the accident, none of that stuff. This is just taking our possible outcomes and it's turning it into a it happened or it didn't happen. So let's go ahead, and for this first part, I'll show y'all how the binary theorem applies to the coin toss. So for example, let's go ahead and say that we toss a coin 3 times. And what I want to know is what are the possibilities? What are possible outcomes and with what probabilities? Now, this is a straightforward enough question to where I think we could figure it out pretty cleverly on our own. So if I take a coin and I toss it 3 times, and we're not interested in the order in which the data comes back, what are my possible outcomes?
Heads or tails?
Heads or tails on any one event. So assuming we have a fair coin, that means that and I'm going to introduce a little bit of new nomenclature, but I think this is pretty straightforward here. The probability, P, of getting heads, well, that's equal to 1/2. The probability of getting tails is also exactly equal to 1/2. So when I say it's fair, I mean that the chance of either side coming up is perfectly 50-50. It's not weighted to prefer one side over the other. But when I toss 3 coins, what are the potential outcomes? I toss 1 coin 3 times. What can happen?
You have the same probability 3 times, so heads or tails
I'm not
times
asking
3.
about
So,
I'm not asking about potential
okay.
probabilities. I'm asking about events. I toss 1 coin 3 times. What data could I end up writing down on my paper?
You could get all tails.
I could get all tails. What else could happen?
All heads.
I could also get all heads. What else can happen?
Three heads, 3
You can-
tails.
You can get 1 head, 2 tails, 2 heads, 1 tail.
Correct. There are 4 different ways that this event can go down. So I can either get 3 heads, or at the extreme other end, I could get 3 tails, or I could end up with 2 heads and 1 tail, or I could end up with 2 tails and 1 head. Now, I want to go ahead and I want to go through and I want to figure out what are the various probabilities that these events can occur with. And with 3 heads, I think that one is the most straightforward. What's the chance that you toss a coin and you get one head?
50%.
One half. What's the
Half.
chance that I toss 2 coins in a row and they're both heads?
25%.
A quarter, yeah. Quarter.
Right, because I would multiply them each time I add an additional event. So the chance that I get 3 heads straight in a row is going to be 1/2 times 1/2 times 1/2, which is 1/8. So the probability here of getting 3 heads, this is going to be purely 1/8. This is just 1/2 cubed. The same here with 3 tails. The probability here has to be that this is going to give me 1/8. So let's go ahead and use a little bit of logic. What is the total probability that I could end up with any case here in the middle?
Isn't it also 1/8?
No, it can't be, because then I would have 3 events that add up to a grand total of 3/8. If I do something that occurs randomly, what's the chance that anything happens? If I go to Las Vegas and I play a game of poker, what's the chance that I play a game of poker?
100%.
That's called normalization or unity. If you have some finite set of elements that are supposed to encompass all possibilities, then the possibility that something happens, right, better be a grand total of 1. When you're done, all of these need to add up to 1. Right? This is just the idea of normalization. It doesn't make sense to say that something has a 200% chance of happening, or that, oh, I added up all the possibilities. The grand total of all the possibilities is 30%. Like, no, man, if you're doing something random, the grand total chance that something happens better be 1. It has to be. So that means that these two in the middle, what would they have to add up to, since this is 1/8 and this is 1/8?
Three-eighths and 3/8.
That's probably what it's going to end up being, but in total, these middle two need to add up to 6/8, right? We want to come up with some sort of scheme here where we guarantee that our grand total is 1, right? Because if I'm going to toss 3 coins, then we're going to get one of these 4 probabilities. So just for the sake of argument, right, how many different ways can I do this? How many different ways can I get 2 heads and 1 tail? What order could they come to me in?
Two orders. Either you get 2 heads first and then 1 tail, or 2 tails and then 1 head.
That's not answering my question. What's the chance that I can get 2 heads and 1 tail? How many ways can that occur? I'm going to toss a coin 3 times. How many different ways can I end up with a total of 2 heads and 1 tail?
Head, tail, head.
I
Tail,
have
head, head.
heads, tail, heads. What else?
Tail, head, head. Head, head, tail.
So would you look at that? There are 3 different ways that this can happen. And I would argue that the chance that we get this first outcome is going to be half times half times half. The chance we get the second outcome is going to be half times half times half. The chance that we get this third and final outcome is going to be half times half times half. And there's 3 ways that this can occur, which is to say that one of these more likely circumstances in the middle, that gives us a grand total of 3/8. Same thing here with my 2 tails and 1 head. This could come to me as tail, heads, tails, heads, tails, tails, or tails, tails, heads. Any one of those 3 outcomes would give us 2 tails and 1 head total. And again, the chance of any one of these individual events occurring is going to be 1/8. So the chance of this here is 3/8. So to answer our question, we toss a coin in 3 times. What are the possible outcomes and the probabilities? Well, there is a 1/8 chance that we'll get triple heads. There is a 1/8 chance that we'll get triple tails. And there is a 3/8 chance that we'll get 2 heads. And there is a 3/8 chance that we'll get 2 tails. This has a couple nice features. All 3 of these add up to 1, which makes sense, because that is to say, well, what's the chance that I toss 3 coins and I get an outcome? Well, you're guaranteed to get an outcome. So it better add up to 1 in the end. Yeah. Are there any questions on this breakdown of this scenario? Is this okay? It's either okay or it's not. Are there any questions out there?
So Mr. Robinson, you just wrote like the HTH and like those pairs just to justify why it's 3/8.
To explain how, like, if a single event can happen multiple different ways, right? Because I'm only considering combinations. I'm not considering these permutations as being separate, right? That as you get to the middle here, there's more ways that this stuff can occur, which makes it more likely that this will be an outcome as opposed to getting a pure triple head. There's only one way this can happen. There's 3 ways that you can get 2 heads and a tails. And in this specific example, it happens to be that there are 3 ways that this can go down. Are there any other questions out there? Okay. Here's how the binomial theorem applies to this and why we're interested in it, and then we'll look at a more complicated example. All that this actually is it's an expansion of 1/2 plus 1/2, then raised to the 3. That's all that we're actually looking at. So here's the deal. The chance that I get heads is this first 1/2. The chance that I get tails is this second 1/2. That's nice and neat because what's 1/2 plus 1/2?
1.
And then 1 cubed is
1.
1. This always adds up to 1, no matter how many pieces it's going to expand out into. And as such, I can guarantee that this is normalized, that all of our probabilities add up to 1. If all of our probabilities added up to 1.5, that would be nonsense. And so I can now use the binomial theorem in order to expand this out, and then we can read the probabilities from each one of the positions along here. So this is to say that this is going to be 3C0, 3C1, 3C2, 3C3. And then along here, I have to tag on certain terms and raise them to certain exponents. What's the rules of the binomial expansions? What are my terms and what are my exponents? If it was x plus a to the 3, then this first one would be x cubed, and then the next one would be x squared times a, and then the next one would be x times a squared, da 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 da. What's my expansion? What am I writing in these parentheses?
1/2 to the 3rd and 1.
All of these parentheses get a 1/2 inside of them. Both of the terms that I'm expanding are a 1/2. And the
Mr.
rule
Robinson, why
is
is it
that
cubed?
the rule is that as I go across, I'm going to decrease the exponent on the first one and increase the exponent on the second one. 3, 2, 1, 0. And for the other one, I will increase the exponent. 0, 1, 2, 3. What was the question out there?
Why is it cubed?
Because that's the rules of the binomial expansion. These exponents sum to this number right here, and the first one gains all of the exponent of this first term. And from there, we count down. For the other one, we count up.
I
And
see.
so if you take your calculator and you process 3C0, you are going to get 1. So this first one is 1 times 1/8. But if you take your calculator and you process 3C1, what do you get?
You get 3.
And then what's 3C2?
3.
And then finally, 3C3 is also 1 again. So whatever way you want to think about it, here's what the binomial theorem does. The binomial theorem, based on how many times you are going to allow this binomial event to occur. In this case, our binomial event is a coin toss, so it's split perfectly 50-50. What this is saying is that if I have a coin that I'm going to toss 3 times, there are 4 possibilities. That's one thing that we can learn from this, because there's 4 terms in the expansion. And it also gives us the the probability for any one of the outcomes along this set, where the first one would be 3 heads. The second one would be 2 heads and a tail. This third one would be 2 tails and a head, and this final outcome is triple tails. The binomial expansion very quickly gives you how many possible outcomes there are and what the probability of any one of the outcomes is. The other nice thing here is that because of the initial setup, because it starts off as being something which is obviously 1, as long as you do it correctly, you know that if you go back across and add up all of the terms in the expansion, they also add up to 1, which is a mandatory fact when considering probability. The chance that something happens has to be 100%. Are there any questions here?
No.
Okay, then let's go ahead and consider a fancier binary event, a fancier question of this nature. Let's say that example 2. The chance of contracting a disease upon contact with an individual is 85%. And in any given day, you contact 5 people. So what I want to know is, what are the odds you contract the disease from any given interaction? And here's the only reason I mean to talk about this. The binomial theorem is far more interesting and far more useful when the binary is not split equally amongst 2 probabilities. So here, this is kind of boring because the probability of heads is half and the probability of tails is also half. So when we get down here for each one of these constructions, it's half cubed times 1/2 to the 0, half squared times 1/2 to the 1, half to the 1 times 1/2 squared, half to the 0 times 1/2 cubed. But no matter what do each one of these clusters simplify down to? They all simplify down to the exact same thing.
1/8, right?
They all simplify to 1/8 for any given event. So the only thing that's interesting is actually the coefficients off of this binomial theorem. And so here, let's look at how this ends up being a little bit different. When it comes to our probability, our binary, we are talking about disease contraction. So the chance that you are sick is what? The chance that you come in contact with somebody and you get sick from them?
85%.
Yeah, whatever this thing is highly, highly contagious. So what is the chance that you contact somebody and you remain healthy?
15.
15.
Good. So that in itself is already you learning to use normalization. probabilities naturally need to add up to 100%, right, if there's no third option. So if you have an 85% chance of getting sick, you can assume that you have a 15% chance of remaining healthy after any individual contact. So here is the binomial expansion that we're being asked to conduct. 0.15 plus 0.85, then raised to the 5th power. Is that okay?
Yep.
And you could put the probabilities in there in either order. I just want to put 0.15 up front so that we do it that way, so that it's a little bit easier to interpret what these terms mean as we move along. So this first one here is going to be equal to what? Just no thinking about what any of this means, just how would I produce a 5th power expansion?
Five
5C.
5C 0.
Oh, I just got that right. Okay.
And then 5C1, 5C2, and then all the way to 5C5.
Okay. So we're going to have 6 terms here, and I feel like I should have probably written it out in bigger space because I'm not sure I'm going to be able to squeeze everything in on each one of these terms nicely. And what is each one of these going to be multiplied by?
0.15 and 0.8.
Yeah, so this first one is going to be 0.15 raised to the 5th, 0.85 raised to the 0, and then we follow that pattern the whole way down. So 0.15 raised to the 4th, 0.85 raised to the 1, 0.15 raised to the 3, 0.85 raised to the 2, plus 0.15 raised to the 2, 0.85 raised to the 3, plus 0.15 raised to the 1, 0.85 raised to the 4, plus 0.15 raised to the 0, 0.85 raised to the 5. And so, sorry that's a mess. I hope that you were able to follow along with that. The answer to this is actually pretty straightforward. What is this first part talking about? Like, what does this mathematical construction represent?
The probability of you meeting 5 people and not contracting the disease.
Correct. This is saying what's the chance that you meet person 1, you don't get sick, person 2, don't get sick, person 3, don't get sick, person 4, don't get sick, person 5, don't get sick. All 5 interactions, you come out healthy. So this is going to be 5C0, which is just 1. Anything C0 is 1. So the only thing of interest here is actually 0.15 raised to the 5th, which is a very, very small probability. So this is 1 times 7.59375 times 10 to the negative 5th. So this very, very small number is the probability that you remain healthy after 5 interactions with a disease that has an 85% chance of being contracted. And for these other 5 terms here, do I actually have to calculate them?
No, isn't it the same?
The same?
The triangle.
I guess
Shouldn't it equal 1?
that's what's up. The fact that all of this has to add up to 1 is what makes it so that I don't actually have to go through and calculate all of these individual 5 odds and put them together. They all mean more or less the same thing to me. This is saying that, hey, what's the chance that you meet 5 people and you contract the disease from 1 of them? What's the chance that you meet 5 people and you contract the disease from 2 of them, from 3 of them, from 4 of them, from 5 of them? last I checked, if you get sick, you get sick, and that's the only part that matters, right? So since we know that, well, this is 1 to the 5th, so in total this adds up to 1, then once I have this term, if the difference between these other terms doesn't really interest me, I know that the rest of these have to be 1 minus this value. So this has to be 1 minus 7.59375 times 10 to the negative 5th. And so this is going to be equal to some version of saying 99%, 0.9999240,625. So if there is some sort of disease out there that has an 85% chance of spreading from one individual to another, the chance that you go out into the world and you have 5 normal interactions with people and you don't get it is this very small chance here on the left. So the chance that you come out healthy after 5 interactions is very slim. The chance that you contract the illness is basically guaranteed. So hey, that's the way in which the binomial theorem is useful to us. If you have some binomial event, some binary event, right? Something where it's either on or off, it's heads or tails, it's sick or healthy, it's accident or no accident, it's 0 or 1, something else that's dissectable in that way. The binomial expansion can be used to very quickly give you all possible orientations of those events, and more importantly, the related probabilities to those orientations. Anyway, that's it for today. So you all have a very nice day, and I will see y'all tomorrow on Tuesday. Yeah?
Yeah, sounds good.
Oh, and by the way, if you didn't upload classwork for last week, please be sure to do that before today is over. Please be sure to upload your your week 10 classwork from last week. I forgot to holler about it. It's already an assignment though on Classroom. Peace, y'all.
All right.
Seems wrong.
Seems wrong.